Hello, my name is Jolnar Al Mousa, and today I'm going to talk about FCC structure or phase-centric cube structure. Is one type of the metallic crystal structures. So let's talk about them in general. So metals are considered crystalline materials, which means that the atoms are packed in patterns, as you can see here, and that will result a higher density, and we call it dense packing because the volume between the atoms is as small as possible. The density is high, and we all know that metals have high densities. Why is that? Well, that's for many reasons. One of them is that because all the atoms have the same radius, because usually they belong to the same element, so they are similar and they can bond. Yeah, they can bond easily. The other reason is that the metallic bond is not directional, which means that the bonding between two atoms does not depend on the direction, which will make the bonding faster and easier between the metal atoms. The other reason is that the distance between the atoms is as small as possible. As we say, that this is small, so the volume is small and the density is high, and the small distance also will result a lower bond energy between the atoms. So if the bond energy is the energy required to bond two atoms, and if the distance between them is small, the bond energy is going to be low, and the bond is going to be easier. So the metal atoms tend to be closer as much as possible to each other to lower their bond energy. So there are three types of metallic crystal structures: symbolic cubic structures, body-centric cubic structures, and face-centric cubic structures. In this presentation, I'm going to focus on the FCC. So the simple cubic structure is the simplest one. The body-centric cubic structure is a little bit more complicated than this one, but FCC is the most complicated one, and we're going to talk about it in this presentation. So since we have different structures, it makes sense to study the different properties that each structure has. Uh, a few important characteristics that we should focus on for studying any metallic structure is the unit cell. The unit cell is the smallest repetitive unit in the structure. That means we can't cut or divide the unit cell anymore if you want to get the same structure or the same repeat pattern. And the unit cell for the FCC is stuff like that. We're gonna talk about it in the later slides. The other property is the atomic packing factor, ABF. The ABF represents the fractional volume occupied by atoms in unit cell. Okay, and it's a fixed value for the structures. For FCC, it's 0.74, and it's the maximum volume that can be achieved. The property is the coordination number, which is the number of atoms attached to the central atom. So, for example, for the FCC, it is 12. So, for a central atom in the FCC structure, there are 12 atoms, neighbor atoms attached to the central atom. The other one we should focus on or study is the number of atoms in the unit cell. Each structure has different number of atoms in the unit cell, and we're gonna need that information for calculating ABF and the density for a structure, so it's very important. So for FCC, there are 4 atoms per unit cell. As you can see here, on each corner of the cube, it's 1/8 of atoms. So since we have eight corners, they can add up to 1 atom. And on each face there is a 1/2 on an atom, and since we have 6 faces, they can add up to 3 atoms. 3 plus 1 is 4, so for FCC there are 4 atoms per unit cell. Example of metals that have FCC structures: aluminum, gold, copper, nickel, silver, and lead. For calculating ABF and density for FCC, we're going to use these equations. So again, ABF is the atom per unit cell times the volume per atom dividing by the volume of unit cell. Now, in the close-back direction, there's a specific relation between the radius of an atom and A, which is the length of the cube to get the ABF. As you can see here for an FCC, this length is A, this length is A, and this length is for R, since there are 4 radiuses here. And at the same time, this line is the hypotenuse of the right triangle, and it equals to square root 2 times A. So that's how we get this relation here for R equals square root 2 of A. So if you substitute all this information in the equation of ABF, 4 is the atoms per unit cell for FCC. Here's the volume per atom, which is considered to be a sphere, which is here. So here is the volume of the sphere for divided by 3 times 5 times R cubed, and we substitute the relation between A and R here. So R equals square root of 2 divided by 4 times A, all raised to the power of 3, divided by the volume of the unit cell, which is a cube, so it's A cubed. And we can get this number, which is the maximum volume achieved. The density of the FCC is going to be calculated by using this formula, n times A divided by V times N, where N at the top is the number of atom per unit cell, which in this case 4 for FCC, A the atomic weight for the element that we are using, V the volume for the unit cell, which is A cubed, and N the Avogadro's number. And if we do the calculation right, we're going to get the density in the correct units for FCC structures. The last thing I want to talk about before going to the 3D models is the stacking sequence for FCC structure. So if we have 3 layers of atoms, A, B, and C, and if our structure is a closed packed crystal structure, FCC stacking sequence will result or it's going to be A, B, C, and it's going to beat again A, B, C, where the third layer, which is C, is going to be placed in the other direction of the first layer A. As you can see here, A and C, they have technically the same, but they are just pointing in different directions. So C is pointing this direction, A pointing to the other direction. So if we add C at the other direction, we're going to get an FCC structure, but if we add it at the same direction, we're going to get the same as the first layer, and the sequence is going to be A, B, A, B, and in that case, we're going to get a hexagonal stacking sequence. So that's all for my presentation. I'm gonna go quickly to show you the 3 model that I did. So this is my FCC lattice model that I created. As you can see, it's similar to the one that I showed you in the slide earlier. And all these atoms are the same. I just colored them just to make it more easier to see all the atoms. As you can see, there are for each 1 atom at each corner and 1 atom at each center, like 1 atom at the top, at the center of the top, the center of the bottom, here the left, right, back, and front. And I'm going to show you different views of it. So this is the trimetric one. This is the top one, the top view of it. So this atom is this one is this one is this one, and this atom is this one, and of course this one is this one in the middle. This is the front, this one, and this is the view from the left. So it's a really good thing to have different views to study the structures. That's all for my presentation. Thank you.